So in this video we'll take a look at a couple problems between 25 and 32. These are a little different because we want to find intervals of not concavity, excuse me, that's chapter 3. We want to find intervals of continuity. So this function in number 29, it has a couple different components that I want to kind of look at. If you look at the inside component, so I'm going to cover up the sine component for just a second. The thing inside the sine function is x squared plus 2. I never have to worry about x squared plus 2 being undefined. It's going to have a real value no matter what I put in place of x. I don't really care about what's inside the sine function. If I also consider the sine function, I can take the sine of anything. I can take the sine of a negative, I can take the sine of a positive, I can take the sine of 0. I have a continuous function here. It's within another continuous function. Number 29 is continuous for every single value of x. And the way that we would denote that in interval notation would just be from negative infinity up to positive infinity. Now 31 is a little trickier because we are going to have to do a little bit more work to figure out the intervals of continuity for this one. The natural log function can't have any old thing pop up inside of it. If you think about the graph of natural log of x, it looks like this. Now this is not the graph of the function in problem 31. Oops, and I'm writing the function in problem 31. This is just the graph of natural log of x. Okay? It has this anchor point or this x-intercept of 1, 0. Notice that it's not defined when x is 0 and it's not defined when x is negative. The only numbers that can go inside of a natural log are positive values. This particular natural log function in problem number 31 doesn't just have an x here, but hopefully you can use our 30-second discussion of this graph to realize as long as what's ending up inside this function is positive, we're not going to have an issue. How do you ensure that what ends up inside this natural log stays positive? Well, with an inequality. You need x plus 1 to be positive. You need it to be greater than or equal to 0. Simple inequality. Could have solved this probably in middle school at some point. Subtract 1 from each side. You get x is greater than negative 1. How would you say this in interval notation? Because what we've basically determined is that as long as x is greater than negative 1, this function is going to be fine. It's going to be defined. It's going to be continuous. There's not going to be anything weird going on with it. So in interval notation, how would we specify this result? Well, we're starting at negative 1, and we have all values greater than negative 1, so all values onward to infinity. We never include an infinity or a negative infinity because we don't quite ever get there. We're not including this negative 1 because we're not allowed to be equal to. And whenever you're writing an interval that doesn't include an endpoint, you're going to use a parenthesis to show that. If we were allowed to be equal to negative 1 here, then you'd use a bracket in interval notation to show that you'd include negative 1.